Um, okay. Well, I'm going to present the paper that I select. Is Cloud Container Technologies, a state of the art review. Basically, the motivation about selecting this topic or this paper was because I'm really interested in this kind of technologies. I'm involved in some type of container development team, so that's why I choose this topic. So what is a container or a containerization? I will define a container as like a box where you can package your software, your application, your scripts, and you can add multiple dependencies right there, your operating system dependencies. Even if your dependencies are like Python or something like that, you can add modules inside, I don't know, Docker files. You can define your entry points, and this can be useful for running on different kind of infrastructure on the cloud, mostly in infrastructure as a service and platform as a service. In the next slides, I will comment a little bit about the benefits that this type of containerization environments, these container applications can be better if you can run maybe in platform as a service, otherwise running on infrastructure as a service. Then I need to define what is a virtual machine, a virtualization inside of the cloud environment. I will say that it's like a machine that you can share your resources with the host node, that you can raise that machine and you can select that amount of resources and still monitoring with hypervisors on all that stuff to try to create a virtualization environment, as well as containers, but well, kind of different because they have, as we discussed in previous sessions on the paper number 2, I think, we have the different topics about operating systems, kernel, that it's well, in containers you share the OS, but in VMs you can have your, well, not the OS, I mean the kernel, and in virtual machines you can have a different kernel. So yep. Then we have the virtualization versus containerization. The topic highlights two different differences between containers and virtual machines. They said that across the multiple papers that the research investigate, they demonstrate that it's a better resource of efficiency of containers compared to VMs. And also they say that are more flexible. I mean, this is a paper of the 2017. A lot of containerization and virtual functions have been changed since that year. So I will say that it depends. I think no one is better than the other one. It depends on the usage that you are giving to each of them. So in my case, at least in my job and my current job, I monitor infrastructure with KVM and, well, the infrastructure as a service part of it with KVM and virtualization functions, but also we run some content with QEMU and libvirt to try to virtualize. But we think this is better on the containerization part of it, I mean in platform as a service, because you can set a pipeline, you can set containers orchestration methodologies to try to enable like a more organized way of the test or applications that you want to deploy. So for me, it's not like virtualization, it's better than containerization, and containerization is not better than virtualization. So I will say that depends on the on the thing or in the application that you wanted to apply. Then we define the container technology principles. The paper mentions some of them. Some of them were really interesting because some of them I didn't know about it. Almost all, not all, almost all containerization applications are based on LXC, Linux containers. And since 2017, they say they were enabling new kernel mechanisms, C groups, and namespaces to try to isolate the OS. So that's really nice. Then we have the Docker build around container engines. That means that you can have containers that can act as portable. That means that even if you have you package an application or a script with multiple dependencies, you can run that kind of container in another system without problem if you have, I mean, the network and all that stuff, but you can run it in even if you are running the container in another physical system or host node. Then the thing that I said that the platform as a service clouds supported deployment applications. Yeah, as I will mention in next slides, you can set a group of containers. You can run multiple containers in parallel. You can communicate between containers. You can deploy containers sequentially and all that stuff that can be pipeline as a code or something like that, that you can orchestrate these kind of technologies. Oh, well, then we have an image about the cluster architectures. It seems like it's like not good, the quality, but sorry about that. But basically, this represents something like that. Here I have a mini Raspberry Pi cluster that I built. So, well, a cluster is a setup of interconnected host nodes that can interact each other. There are multiple ways to interact, but basically that's the definition. Then we have the host nodes that are like physical machines, everywhere that you can run the containers, that you can run any kind of, well, where you have an operating system that you have, you can run application like a computer, I mean. Then we have the most interesting part of it, that is the container by itself. In the containers, as I said, we have multiple like configuration interaction with containers. You can see here in the first node, in the up right node, that we have 3 different containers. You can scale up or scale down your container applications. I mean, that's the service. Then you can, these pointed lines that we have across host nodes are the interaction that you can have between containers. We have seen that in previous expositions, like in the Kubernetes exposition that we have, that I mentioned that I didn't know that containers can communicate each other, even if they are running in a single machine or even if they are running in multiple machines. So this is the link. This is a really interesting application. It can be by localhost, and it can be by the port that the container has. And then we have the volumes. The volumes, the paper highlight the importance of volumes, such as the storage. But I think you can use volumes in a different way. I mean, if you share volumes about the devices that you have in your computer, you can use that specific device. I mean, LSPCI, well, PCI devices such as Ethernet cards, or even, I don't know, different type of, oh man. Can you hear me? No.
Yeah, we can hear you.
Yep.
Okay, so sorry. You can share multiple devices, and yeah, that's the way. At least in my job, we share some volumes like dev that you can have on depending on your operating system, and you can apply multiple applications with these type of devices. I mean, you can stress some devices, you can interconnect and ping other devices between each other, and that's nice, I think. Uh, as I said, the container has like an architecture. You need to put like, well, I don't know if you can build a container without an operating system, but at least as far as I know, you need to put a base image for your operating system, and you need to you will share the same Linux kernel that you have, and all the same things that I mentioned. The writable container, well, there is a part really interesting that mentioned on the paper that I didn't notice, that it's the writable file system that once you like create the container by itself, the base container, and then if you modify a layer, or I don't know, you add some dependencies in the Docker file or something like that, that is adding a layer, you overwrite that type of base container image, and that's why it doesn't take so long. I mean, if you download an OS, it will take 30 seconds or something like that, depending on if your computer is really, really quickly. But if you have already charged that layer on the base container image, will not take that long. So I didn't know, I did notice about this type of things, but I didn't know why, or the name. The name is writable file system. So okay. Then we have the container summary. The paper touch like a resume of the things that uh, are more important. They say that, well, you can deploy even in infrastructure as a service and platform as a service, but it's more efficient, or not efficient, but it's more used in platform as a service than in infrastructure as a service. They mentioned that the importance of, as I said, in my current job, we use the virtualization part of it with virtual machines, I mean, and we use for infrastructure as a service, and the paper highlights that part really, really nice. I think also they highlight the importance of the usage. They use single container solutions. They think you can grow solutions for cluster. And we have some concerns about the performance and the resource utilization. I think nowadays in 2022, this is not anymore a concern, at least in resource utilization, because you can define in Docker, you can see the image right there. Docker is the most used container application for containerization. So you can define in Docker even the resources that you want to use. So at least in 2022, in the few experience that I have, this is not a key concern. So yes, and then you have it. Docker is the winner, is the most used container application since this paper relates 2017 to 2022. So yep. Then we have the container orchestration. This is really interesting for me because this is the way you can manage your distributed clusters, but it's not only turning on and off the applications or monitoring the containers that you have. So it's more like that, more than that. You can coordinate the container deployments, as I said, in parallel, sequentially, scaling pods. You can define the network inside of containers, the availability of the workers that you have in a cluster. So container orchestration is a really, really important part of it. And in my current job, the orchestrators made the CI/CD. I don't know if it's defined that the orchestrators made all the CI/CD, but at least in my job, all the orchestrators are mm, are working on this type of continuous integration and continuous deployment environments. We have multiple container orchestrators like Kubernetes, Key-Tree, Micro Kubernetes. I'm using for this cluster Micro Kubernetes because it's the lightweight version of Kubernetes, because you need to configure a lot of C groups and a lot of things to try to enable it on Raspberry Pi. So I decided to use the canonical version from Micro Kubernetes, and it works really, really fine for making the deployments with the YAML files and all that stuff. So K3 is from Rancher, so is also an orchestrator. It's a lightweight, and I only put Jenkins because it's the way that we continuous integrate and continuous deploy. Basically, we have here the systematic mapping study, that it's all the papers that this research takes for defining some definitions. This consists on 46 studies from 2007 to 2016. There are not all the papers of 2016 because it was like they need to present the paper and they put the at the middle of the year the research. So yes, they have multiple categories that I will explain in the next charts about architecture, management, and tool platforms and technology. Here we have the chart that I said. Not much information. You can see that the trend is that the papers and the trends of container applications are growing each year. This was like at the middle of the 2016, so we can cancel this. But yeah, the trend is moving forward to more and more research about these topics. And here we have the chart that I said. We have 3 different, I will say, topic stages. One is from architecture, that is more focused on the development stage. We have the management that also focus on the development, but also in the operational stage, and the technology that it's about the technologies and resources that we have for containerization. And you can see here that the trend of all the 46 papers, 40 talk about Docker, and only 21 talk about Linux containers. Even if Docker is based on Linux containers, they are talking about more as infrastructure as a service, but it's like quite balanced with platform as a service in cloud service models. And another interesting part of it is about that the papers in the architecture stage talk more about the deployment than in the development. So yeah, also we have the technology stack, 5 different categories about the topics. Some topics can touch 2 or more topics, but I mean, this is like the way they differentiate the categories between the papers. So yeah. Here we have more explained or more visual. I mean, each of the categories that we have. The deployment part of it. Where is it? I think I didn't put that chart, but there was a chart that it was talking about more about the deployments, but that's okay. Well, this was really interesting that container technologies are talking about more in the cloud and big data, and also in the distributed systems. I have never seen containers between the distributed systems maybe Maddie can confirm. He's more an expert. So I don't know. Most
I don't
I
get
lost
it.
audio.
Study distribution by community. You mean 49% of 49% of the papers are talking about cloud and big data? Or I don't get that figure. The study distribution.
Yes.
You mean the 49% of the papers? The study comes from.
I mean, from the 46 papers, some of them can touch different topics inside the same paper, but the trend is more like oriented to cloud and data. I mean, in the figure 5, you can see that of the study distribution, and for each of the graphics is the same. Yep.
Okay. Okay.
I don't know.
I'm
I don't know.
confused about it, but
I think I put another slide, but well, I don't know. Okay, well, I will have this. Okay, well, I don't know. You have some questions?
So, question answers. I think Rodrigo is managing.
Okay.
Well, first, are there any specific questions for the presentation before I go on into the ones that I added that you want to ask Alex or any one of us?
Yeah, just one quick question. When you saw the result from who was the winner, were you surprised or did you expect that?
Well, I'm not surprised because there were some different container applications, but I didn't know even the names. I get surprised by the that some of that there are some different type of containerization. Well, different applications for the containerization like Rocket and all that stuff, but I have never used because I mean the industry standard is like Docker because it's open source and all that stuff. So I didn't get surprised. I mean,
is Docker open source?
I mean, yes, isn't it?
Because right now they are like
you will have
some...
Yeah, but I think I mean you have a certain amount of storage in the registry, but if you want to increase that amount of capacity in the registry, you need to pay. So yes, but it's like
I mean, it is open source in the sense that you can go on and see the Docker code, right? I mean, you can go on and contribute on the Docker repositories to, like, I don't know, like be a contributor and throw in a pull request and so on.
I don't know. I can barely hear you. I don't know if I am the only one or...
No, probably it's me.
I was able to hear just fine. But what he said, just in case, really quickly, it's open source in the sense that you can go and look at its code and fork it and create PRs and everything you want. Like,
okay.
Like you can actually like see the Docker GitHub repository. Like if you look for it, like, I mean, I don't know if this is actually it, but it probably is. I just shared it in the chat. So like, yeah, like if you want to, you can fork it, create PRs, whatever.
Okay. I have a question. Why you didn't put Docker Swarm in the orchestrators?
Well, I didn't. I have never used Docker Swarm in my experience. I only have used Kubernetes. So maybe because I didn't. It was not in my mind. But well, you're right. Docker Swarm is another orchestrator.
Okay.
Yeah. So any additional specific question from the presentation? If there's not, then I can go on with mine.
Yeah, not really, just a quick comment. When he was talking about about the volumes, right? One cool thing that you can do with volumes is have a consistent development environment. Like you can create an image that has a bunch of tools installed. And then you can actually use a volume to point it to your local file system. And then you start the image and you SSH into it and start the container, sorry. And all the changes you do inside the container are actually reflected in your local file system. So it's like kind of similar in philosophy, I guess, to like Python's poetry. Like you have an environment that is self-contained. So some companies use like these development environments based on containers, which is a pretty cool application of volumes when you were talking about them.
Yeah, that's right. I mean, also, I mean, there are many places in which, for example, so that you don't need to spin up a Postgres database. You can go on and spin up an image of the Postgres database and drop the file system from the database to a volume, so that whenever you spin up that Docker image again, or even if you delete it, you can mount the volume again and you continue to have your database. But you don't need to install all of the Postgres or all the Oracle DB dependencies. You just have it.
Yeah, and there are containers for everything like Postgres, Mongo. Like I've been playing lately with Mongo. I don't have that stuff installed on my computer, but you can actually like spin up a cluster of Mongo like with replica sets and sharding and everything you want all in your computer. Like you just need to assign them different ports and they can talk to each other and you can find them. And like in the end, you do like Docker compose down and it's just gone. So yeah, like I was at some point I was looking at some document and it referred to containers as throwaway computers, which is like a pretty neat way to think about them. Like you spin up a computer, you don't like what you're seeing, you trash it, like you create one again. Like it's super amazing.
Yeah, you're right. That's it. So very in the same line of what Ricardo was introducing, I was going to ask you if you really experienced how the containerization affected your job as a software engineer. I mean, were you those people that really experienced at first hand that migration from virtual machines to only containers? And did it improve your development experience, or for you it was just like what it was already available there? I mean, did you really suffer that migration?
I mean, for me, the main impact was like before, if I wanted just the example I gave, right? Like Mongo, I was like, okay, how the hell do I install this? How the hell do I set it up? Like how much space do I want to set up in my disk for this? Like just thinking about using a new tool was like kind of daunting. And now it's like, let me see if there's a container for this, right? And there's containers for everything, like for Mongo, for etcd, for Postgres, like for pretty much everything you can think of, there's a container. So like it improved my kind of like my local development experience a lot. Like just knowing that I don't have to actually install stuff, but I can just like spin up a container and then they just tear it down. Because like as most of us probably know, like you're running some Python, right, or some whatever, and you're missing a dependency, and you do like naively you do like pip install, and then that works, but then some other part of your setup is now completely messed up because like whatever pip did like completely nuked the original dependencies. So that is kind of scary, and I don't really like installing stuff in my system. So containers are a beautiful way for me to run things without actually having to install things persistently, which I just love.
Thank you for that, Ricardo. So yeah, I mean, I have experienced that firsthand. Anyone else? I mean, have you ever, or are you still like a little scared on the Docker end and really do prefer to install stuff locally on your computer and not going into containers, at least for local development?
It depends what type of development you're doing.
I mean,
a lot, because if you need like an entire framework, like if you want an entire platform, for example, that you want to call microservices or things like that, or if you want to test a single like that it's isolated, how do you say, a microservice, you know that you don't need a lot of things. It depends, right? Because like, for example, if you want like the entire Amazon platform and you want to execute it and you want to see how everything is interacting, the data flows, the logging or whatever, okay, you need an orchestrator and containers probably. Well, that's probably the easiest to isolate all the information. But if you only want to test, like for example, you are creating an API, for example, and see how it responds and things like that, but not, well, if you have a database, probably you don't care that much. But if you don't have that much interaction with other microservices, then you don't need it, right? Like it depends, because all the day I'm between working with containers and not working with containers, and it depends on the use case.
Yeah, you're right. Yeah.
And also, other thing about containers, like even not only on web, like I use it a lot in embedded systems, for applications installations and different type of ownerships, let's say. To it doesn't work exactly the same as in web, but it's similar. And also you try to bootstrap like as much as you can. So instead of having a lot of containers available, usually it's the opposite. You have a container that it's empty and you start adding, because if you try the opposite, then your embedded system is going to use more memory than that you want. And for example, another framework is MiniJL. That is the one that I have used a lot for embedded, to like share it.
Yeah. So if there's not anyone else,
Only as a quick
yeah.
comment. The most used application that is in a container is Nginx, and the most difficult that I have seen it can be easily installed in a container is Elasticsearch. Well, all the Elastic stack, I mean,
Yeah.
Logstash, Elasticsearch, and Kibana, you can pretty much set up with containers rather than make it manually, and it's more easy. You can save a lot of time.
Yeah, I mean, I did that I roll up an elk stack in like a day. So yeah, I mean, it is very easy to, I mean, whenever there is like more container aware or really focused onto it, it is extremely easy to spin up stuff. When it's not, and you need to create like your base image and start installing stuff, it can be a little daunting, let's say. Yeah.
And sometimes, just by experience and last 2 months experience, is that the new AMD M1 and M2 chips from Apple are super annoying.
Yeah, you're right.
I just got the computer and it's a painful now. Yeah, like with containers and all the packages, just saying.
Yeah, I mean, I will talk about that just in the last question. So yeah, going into the next one, we have seen that Docker is basically everywhere, right? But apparently is not making tons of money. I mean, there were already reports on it not going public on the stock market, and also I was seeing just some articles on it like going broke and like firing people. Why? I mean, what are your thoughts? Why is not profitable, and how can you really make it profitable? I mean, and the big question is, in which way would you pay for Docker? I mean, what would it have to bring for you to really pay for it?
They have the hub, right?
Sorry?
Docker has hub.
Yeah, Docker Hub. That's the one that they really get money from. But other than that, I mean, because whenever you're already in the cloud, you already have like their own repositories.
But they have also support.
Yeah, support.
So you have enterprise support.
Yeah, like
but also, I don't know if GitHub has an action about containers that you can store in GitHub, isn't it? Well, I'm not sure, but
yeah, you have the actions. But either way, like he's saying about Docker, right? Because the other is GitHub.
Yeah,
GitHub I mean, in containers. Yep. I mean,
so yeah,
I'm not sure.
So basically, they already have that as a profit, right? As a revenue way in their Docker Hub. Support could be one, like Canonical is currently doing. Any other way in which, I mean, you could say, okay, I would pay for this. I would really like go into Docker and say, just bring this in, and I will pay for it, and I will like give you money.
I think that they have also special projects thing, because I think that when you want to request something new, you can, as an enterprise, you can ask for it. I think I cannot remember that. that somebody did. So it's, and also I think that, I don't know if it's Docker, but either way, like people can profit with that project because of auditing or something like that.
Okay, yeah, that would be nice. Like reaching up to them to say, like them saying, I'm open to requests. Go on and place your bid, and I will let you know if I take it or not. Any other suggestions?
Or maybe if you have I don't know so much interest from enterprises, and you make like a package like all these companies like Microsoft, that you put several products and you can have like a license for your enterprise. But if you use like an user for academy or I don't know personal, you can get a free trial of I don't know 3 months or something like that. Could be another one. I don't know.
Yeah, that
There
also,
can be some
also be nice.
options.
I mean, what would happen if, I don't know, tomorrow you go on, build, do Docker push, and it says, hey, your free license is gone. You need to pay if you want to still pushing images. Would you pay?
I mean, I don't want to pay for Docker, but at least I'm sure that the enterprise that I work, it will pay for that kind of licenses, because we have licenses for so many products, so Docker can be a problem.
I got confused on that part, right? When you say like pushing Docker images and things like that, because that either way it's from Hub Docker, right? Because that's a storage, and actually it's like GitHub that you have X amount of public repositories, some amount of private repositories, and you don't have some set of rules. When you have on Hub, actually it happens a lot with us. That suddenly we have a lot of images built, and we have to start deleting them because we're having a tons of the same image, because each time that we make a push, we build a Docker image to test.
Yeah, I mean,
You know.
but let's just forget about the push one because it's like already actually being paid for, but build,
Yeah.
right? I mean, what will happen if you go Docker build and it says, hey, you have already built 1,586 times. You are done. Pay if you want to continue building.
But the building usually is not local.
I mean,
on this
yeah,
push.
but I don't know. Let's just figure out that they always need an internet connection for you to actually run that. Like Adobe did back in the day when it started with Photoshop, so that you don't copy.
For sure, they will charge, because that's like processing, right? That's the most expensive part of the system. So, yeah, of course, they will charge.
Yeah, but
Yeah, but I mean,
think
if at some point they do that, it's like they're pointing a gun to your head, right? Like companies depend on Docker, like
yeah,
microservices-based companies. So at that point, either everyone will pay, like at that moment, everyone will pay and will start looking for whatever is the next best thing that is still free. Like
yeah, and that's the point. We are talking just about Docker, but the reality is that there are a lot of other tools that can do containers.
right.
So
Yeah.
You just said it. Other tools.
yeah, but at the
Like
point that
like
at the
naming,
point that Docker starts charging, people is always avoiding to pay, always. So at the moment that Docker starts charging,
They will crash.
they're going to find a way for trying to avoid that payment, or they're going to try to look for another tool that is going to do the same. It's the same that is happening with WhatsApp, you know? When
Yeah.
WhatsApp is down, everyone is like, yeah, Telegram, now we're going to Telegram. Then WhatsApp is up again and everyone forgets about Telegram. It's the same that is going to happen with containers. If Docker start asking for money, people is going to, well, there is another tools that maybe, because it's the same that with WhatsApp. Once WhatsApp is down, everyone is starting talking about the thousands and thousands and thousands of amazing things that Telegram has, right?
Yeah.
And say
But what about
they are better than the WhatsApp because of this, they are better than WhatsApp because of that. And it's going to be the same with Dockers.
But what about if the Docker Mark Zuckerberg start to avoid another container technologies such as Meta avoid Telegram and try to monopolize that kind of market?
Well, there are rules. There are rules in the market that they're going to try to avoid that.
I mean, it's just for us to know that we as software engineers, we should, I mean, Docker is great and whatever, but we should really don't look for it. I mean, we should like really be aware of what else is in the market, because I mean, I'm not expert either, but whenever it says like, yeah, there are other tools, like, and if someone comes near to me and says, yeah, tell me 3, I would be like, yeah, let me get my computer, right?
And also, for example, only for storing, if you're not able to build locally first, you are removing the power of testing, right?
Yeah.
But also when deploying or storing, as I mentioned, like Hub, it's only a storage system. There are other ways you can store your own Docker images actually. So it's not that you need it, right?
No, not really. I mean, is that just, I was like just trying to push you guys into say, is it Docker that necessary that you would pay if it starts charging you for it? But I mean,
Nothing is that necessary, not developers.
Okay, let's just move to the third question, because I have already took a lot of time from you. Let me share my screen quickly and see how I can to begin with. Are you sharing, Javier, todavía?
No, you can go ahead and share.
Yeah, sorry. Share screen. This is whiteboard advanced portion of the screen. Share. Okay, I see. Just a second. I think I need like to adjust it. Sorry.
It's loading.
Yeah, sorry. It's that it didn't allow me to like share everything. It just allowed me to share a portion of my screen. And this is because I have like not the permissions to try. I believe. Just a sec. There we go. Are you already seeing it?
No,
Not yet.
No.
It's coming, I think. Maybe give it a few seconds.
Probably.
not really.
I will
maybe
share again.
you have more than one.
Yeah, I have to. I
monitor?
will just drop the second monitor for a second, right?
Okay.
Yeah, there we go. Just dropped it. And just let me get that window back. It should be this one. Okay, I have it here. And then let's go with Zoom, share screen. Basic. Now this is the whiteboard, right? You're not seeing my
Yeah,
screen. No.
Yeah, we could see.
You could see my screen? Or
Yeah.
We were able to see it.
But you only see the whiteboard, right? You don't see
Yeah,
the
whiteboard.
you don't see no, this is not. I don't know why it doesn't allow me to.
You're drawing.
Yeah, no, I didn't want to draw. It was advanced. I would say like portion of the screen. Sure. Okay. Now, what about now? Are you seeing?
No.
I'll start sharing screen.
Yeah, but it's normally that is done.
And it's not the resolution.
No, I don't know. I got everything.
It's not the resolution, like that you have high resolution on your monitor and you have to.
What are you trying to share? You can.
I will just send you the link and we can discuss it. It's better.
Yeah, you can send link. I can share it or.
Yeah, thank you so much. That would be better. So basically, I will show you some Google Trends about Docker. And the thing that I wanted to get you at, if you look at those trends from Google that I found interesting, is one that there is a ton of Google search from people from China looking for the Docker. I mean, if you go towards the bottom a little bit, there, as you can see, China is the one that has the greatest search of the Docker term. They're the one that is the strongest, and also St. Helena, well, right? It has 55 that is in a scale of 0 to 100 search interest. Meanwhile, in Mexico, for example, we have like 8, I believe, or something like that, right? 6. Okay, so what do you think? I mean, about China doing that much research on Docker? Is it only like denser wise, or do you believe like China would be like really power up Docker stuff?
I'm more concerned about what is St. Helena.
Yeah, I
Yeah,
mean,
right. Where is Adelena?
I don't know, but I mean, I was like, yeah, I just went on and checked China, and I was like, why China has so much?
Okay.
No idea what is it.
You know the thing with China? The thing with
But-
China is they never. It's the same that is happening with Bitcoin. They don't want to use nothing created by other country. They always want to have like their own tools, right?
So you
So
think
maybe
they are just,
they are developing some kind of containerization tool,
for their own Alibaba cloud?
something like that. Yeah.
Yeah, I mean, it's
Yeah.
just like,
They are trying to copy it.
Yeah. I didn't want to say that, but yeah, you say it.
well, yeah, I mean, it is one that we should like take a little more care on. I don't know if they will be taking over Docker soon. So again, I mean, if you see it that way, probably the next clone you will be looking at from Docker will be Chinese.
Yeah.
And what happened if you investigate the distribution of software developers in the world?
That's the one that I was just talking about. That probably most of the search terms come from there because there are more software developers there, right?
Yes, because that it matters, right? The distribution.
Yeah, it does matter a lot. I mean,
I
and
was
what-
expecting see India there, and it's not.
No, it's not. That's interesting. I mean, in both senses, either because it had, I thought one, because it supposedly has more software engineers, or two, because they basically.
But
do-
that's weird, right? Because not even USA is there.
No, yeah. Well, not in the top, right?
Yeah,
When
in the top.
you put it in the city, then you can see Mountain View is the top.
Yeah, and
Yeah.
that's expected, right?
Yeah.
Mhm.
And Shenzhen is in the second place. Shenzhen is in
And
China.
Shenzhen, yeah.
Right? Yeah. I mean, and if you like go on and really try to play with these ones a little bit, one of the most searched terms right now in Docker is running Docker on M1 MacBooks, right? So yeah, I mean, it's a problem that we're all experimenting, and we software engineers are.
Painful.
Yeah, I mean, so just as you know, we're not alone, and Mac does need to do something for us to continue using that. And another web page that I wanted to share, this is the last one, I promise, is this one that I just sent Maddie.
Can you guys see?
It takes a little time to load. Or it maybe
Yeah,
doesn't.
it's got it.
No.
Supposed to see something?
Yeah, it's supposed to be loading but it does take some time because it is like a big analysis.
Yeah, because with me only says patents 16,000 and it says like IBM, QA Leuven,
Yeah, there you
VMware.
are. Yeah, you can share with us that part, but basically the important part there was that IBM is leaving.
You can go ahead.
There you go. So will you go?
You can see it, right?
Yeah, or seeing already. Thank you.
What should I do?
Can you go towards the bottom, please? I just want to go into the charts. Well, there, the one is that research has become slower on Docker. That's interesting. So, I mean, on the other end, when we were looking at the other paper, we were seeing that we were actually increasing, but as of right now, you can see clearly that it has slowed up a lot. And since 2018, it was when Docker announced that it was not doing well economically. So people are already like, this is not, they are already looking at other ships to take.
Alternatives, huh?
Yeah. And also if you go like a little towards to the bottom and onto the enterprises, see there, IBM has everything in all fields regarding Docker. So what do you get from that? I mean, IBM is buying Docker, IBM is behind Docker, and what the hell?
That's quite interesting observation, really.
I mean, because I don't know. I mean, maybe whenever it gets like enough not popularity, they go IBM goes on and places an offer.
Does a person from IBM start a Docker?
I don't know. That's one that we don't know either. I mean, because Docker is like, okay, open source and let's keep it, and we are no company, but maybe it's IBM in the back. I don't know.
Yeah, but
Or
a lot of the
one of the first adopters.
a lot of the Docker source the open source projects are, some big companies are behind of them because they have like even if it is not profitable for the tool by itself, some companies are making profit of that, right?
Yeah, you're right. You're definitely right. I mean, also let's also remember that whatever is in research is not what we have available for developers right away, right? This is like the future. I mean, if we go on and read like IBM papers on Docker, we should get some predictions on what Docker will become in the next 1 to 2 years.
Well, that can solve your question. You see that the authors there, you can look into them into LinkedIn and you will see they are working for IBM.
Yeah, that's true. I mean, I just shared this with you so you can go on and start deciding which Docker or container technology you will take afterwards when Docker is gone. They start.
Mexico, no? No pares for jurisdiction.
Yeah, we don't have anything. Yeah, that's not it.
The publishers. Okay. If you want to
Yeah.
find something about Docker,
Go
you
to
know
I-
where to go. Okay.
Okay, that was quite interesting. I don't know if there is any other comments, question. If not, so we can have like 5 minutes break to come back like 7:42 to continue with the second paper. Thanks, Javier. Thanks, Rodrigo, for the discussion. So we come back 7:46 to continue.
Here it is. Can you see this Polar FS?
Yes.
Yes.
Okay, cool. Oh no, that's not the one. This is the one. Okay, cool. Yeah, so I'm gonna talk about Polar FS. I really like file system stuff. I really like this part of distributed systems, like distributed file systems. I find it to be really interesting. And this is a file system that was designed for the cloud. So it's not like so much talking about cloud technologies, or this is more about the cloud architecture gave rise to this thing, right? So we're gonna discuss this and how it's related to the cloud. So essentially Polar FS, as it says here, is an ultra low latency and failure resilient file system for shared storage cloud databases. So Polar FS was developed by the people at Alibaba. They offer it as part of their Ali Cloud, I believe. They have something called Polar DB. It's just a database, like a database that works on distributed like commodity computers. And the way they make it work like faster and better is by developing this Polar FS. So essentially, there's this trend in cloud computing, right, about decoupling storage from compute. It gives you a lot of flexibility and capabilities, such as you can have different hardware for storage and compute nodes. Like for instance, maybe like it's not the same having like a machine that can like put a lot of throughput to a disk than a machine that can do like 1 trillion teraflops per second, right? Like they are different needs. And thus it makes sense to separate the needs of the application with different hardware, right? Then for storage nodes, you can have disk pools, which helps with fragmentation and with a bunch of things. And there's no local persistent state, right? Like you have you have, I don't know, your EC2 instance. Like instead of having the persistent storage there, like it's somewhere else in some DynamoDB table, database, whatever, it's not there. So migrating that data is easier, right? Like it's not sitting in your local machine, it's sitting like in some dedicated machines. But this has some drawbacks, right? Like distributed file systems like HDFS, which I believe is like an open source implementation of the Google file system, have a latency that's much higher than local disk. And this trend continues. Like if you run relational databases such as MySQL, the performance hit is really big. And the main problem here, sorry, these are just like slow, right? Like these file systems are slow, basically because they're using like an old IO stack, right? Like old, I don't know, libc stuff for using for doing the kernel space calls. So cloud vendors provide this thing called instance store. So basically instance store is like you have your EC2 instance and you do have some storage within it, right? Like you have, I don't know, a couple terabytes of disk, a couple gigs, I honestly don't know, but essentially you have your compute node and you do have some local storage. But the problem here is that you cannot put like a full-fledged database on that machine storage, right? Like it's just too much. So there's limited capacity. There's low resilience to disk failures because I don't know, like probably it doesn't have like RAID in it. Like maybe you get a disk and that's it. So if that disk fails, you're out of luck. And general purpose file systems like ext4, they do a lot of their work in kernel space. And at the speeds that these guys are working, the traps from user space to kernel space are actually a bottleneck. So something that we give for granted, like when we study about Linux, like you do your stuff in user space and then system calls go to kernel space, that is actually a bottleneck for these guys, right? Like they're doing things that fast. So the solution to these new problems is PolarFS. So PolarFS, as I mentioned, is a distributed file system. And it essentially, like, it's a distributed file system, just like Google file system, but it is novel in the sense that it uses a lot of hardware technologies. So it uses this NVMe SSDs. NVMe non-volatile memory express is an interface specification for accessing non-volatile storage like SSDs. It can move like 2K megabytes per second as compared to SATA's 600 megabytes per second, as far as some documentation I found. This is per lane. And I believe they support like 16 lanes. So it's like, I don't know, a ton of information per second. So just to compare with these SSDs, regardless of these SSDs, the old kernel IO stack needs around 20,000 instructions just for a single 4 kilobyte IO request. Like these are just machine level instructions, not like C lines. But still, like 20,000 lines for 4 kilobytes of IO, that's crazy. So they're using this thing, which is faster, and it's in user space, apparently. And they're using this RDMA, which is like remote DMA, direct memory access, which allows one computer to access another's computer directly without going through the CPU. So it's like super, super fast. So the example I found is that transferring a 4 kilobyte packet takes like 7 microseconds. Which is way faster. I mean, it didn't specify how much faster, but it's faster than establishing the TCP connection and actually transmitting those 4 kilobyte in packets. Like just accessing the memory is almost like accessing it locally, right? So a lot of the work here is done in user space, which avoids the trip to the kernel, which is kind of the bottleneck in here. So the architecture of PolarFS, it has 2 layers. It has a storage layer that deals directly with disks, and it provides databases with volumes, and it deals with everything related to actually storing the stuff on disk. And then there's the actual file system layer, which supports file management in the volume, mutual exclusion, synchronization, of storage access, etc. And it has a few other components. So libpfs, it's lightweight user space file system implementation. And crucially, it provides POSIX-like APIs. So the idea is that it should be fairly straightforward to replace. Like you have a database. That database most likely uses like libc or some kernel library. So this thing uses very similar APIs. So the idea is that you can like plug and play, well, almost plug and play this new library and like this new file system, and most database systems should be able to take advantage of it. Polar Switch is essentially like a router. It's a daemon that takes IO requests and sends them to the appropriate chunk server. What's a chunk server? Right here. A chunk server is essentially a process that manages a standalone SSD, a solid state drive disk, and manages chunks. So basically, for each drive, there's one of these chunk servers. And then a chunk server manages chunks. So what the hell is a chunk? A chunk is essentially the minimum unit of data distribution. It lives in a single disk, and its replicas live in 3 distinct chunk servers. So I actually don't remember the size of the chunk. I think it's like it can go from like 1 gigabyte to 10 gigs or something like that. But essentially, like it is the unit of redundancy, right? Like when you have replicas, you replicate at the level of a chunk. So you replicate a chunk in 2 or more different chunk servers. And within a chunk, like doing 1 gig of IO every single time you want to like insert a row in a column would not be feasible. So this is further subdivided in blocks. So blocks are 64 KBs. So this is very similar to how our disk works, right? Like our disk has 4 kilobyte blocks. And like, even if you write just 1 byte, like you actually write the whole thing right down. But essentially like 4 kilobytes is relatively a decent size for like our own computers. These guys decided on 64. So the idea of these sizes is that this system needs to know, essentially like a file system in the end, it's a directory, right? Like it knows which files live in which blocks, right? Like it just knows that data. It's essentially its job, right? Like knowing which file lives where. So by using these chunks and blocks, they actually minimize the amount of metadata that the file system needs to take care of. So it's like 883,000 pieces of metadata, which is like relatively a small amount of data, to be honest. So that's about the chunk servers. And then Polar Control, it's a control plane for the cluster. So it provides node management, volume management, metadata synchronization, etc. So just so that we get briefly an idea of what we're talking about, let's check out the lifetime of a write. So like PolarDB makes a write request, right? Like it does an insert into whatever. So this request goes to Polar Switch. Polar Switch, we mentioned it here. It's this daemon. So it actually uses libpfs, like the implementation, like in code, it's an API exposed by libpfs, and libpfs essentially delegates it to Polar Switch. And there's a ring buffer, right? Like I didn't quite mention this, but there are many ring buffers. So the libpfs puts stuff in one end of the ring buffer, and the Polar Switch is reading stuff from the ring buffers. And there are many threads, and this can be parallelized like crazy, right? So Polar Switch notices that there's an entry in the ring buffer, and sends a request to a chunk's leader chunk server. So we're already talking about leaders, so this should be like some foreshadowing that there's some consensus protocol going on here. So in the architecture of PolarFS, there's one leader, and many followers. The leader is the only one that can serve writes, because it needs to coordinate and ensure that the writes fall in all the replicas. But then all the slaves can, including the leader, can serve reads, right? So since it's a write, it goes to a leader. And this is part of where things start getting interesting. Instead of like putting it in some queue that requires like some kernel space logic to put it into a buffer, and then like some other user level call, like user level trap to kernel to read that request, it all goes through DMA, through remote DMA. So basically, the Polar Switch writes directly on the leader's memory without going through the CPU. So this is like really important. We just saw that it's faster to do it this way. So the leader will put it into some pre-register buffer. Then some thread will notice that there's something in this buffer. So this request is processed by an IO loop thread, which writes to the log block and propagates the request to a follower. So at this point, I believe it's not, well, I don't believe, I know it's not committed yet, right? Because it needs to go through some consensus. So it writes to a log block and propagates a request to a followers. So just as before, this guy propagates it to the RDMA network interface cards of all the followers. Again, not going through a CPU. This is all just like going straight to memory, which is like blazing fast. And then they do something similar. They add it to a replication queue. They write the request to disk, and then they acknowledge to a leader, right? So at this point, when a majority of the followers acknowledge the request, the leader can commit can commit this. And like part of the wrapped protocol is that once the leader commits it, it sends like another heartbeat, like at some future point in time, and so that every replica also commits it. But essentially, by here, the data is persisted on disk. So at this point, the leader can just say to Polar Switch, "Yeah, I'm done," and Polar Switch marks the request as done, right? So if this was like this request has been actually committed on disk. So this is kind of like the image. PolarDB uses libpfs. It writes to a ring buffer. Polar Switch pulls it. Then there's this writing to a buffer. This thing like writes to a log. Can you see my cursor? I'm pointing at stuff, but okay. It writes it here. Then it goes back to the RDMA NIC, and it goes to the RDMA network. So you can see there's like 5 and 5, and these are the exact same numbers because this is happening kind of in parallel in the chunk servers. This is the leader. These are the followers. And yeah, so they do this. They send back the acknowledge, and once the acknowledge is received, this actually persists everything. So I guess this is like a pretty standard distributed file system structure. Like there's a leader that handles requests, and then there's a consensus protocol. But what's novel here are these two parts, right? Like this using these RDMA and this SSDs, right? Like this is actually taking advantage of all the low latency hardware. So now, I've mentioned this a couple times. This is a consensus protocol. So when we talk about consensus protocols, there's usually two that come to mind: Paxos and Raft, which are essentially the same. Just Paxos is for crazy people, and Raft is for normal people. So Raft has a problem when it comes to this. Raft is designed to be serialized. So the way Raft works is I write an entry to the leader's log. The leader propagates that to all the followers, right? And well, by the way, there was a leader election and all that stuff, part of the Raft protocol. So it propagates the right to all the followers. The followers write it and then reply back with an acknowledge. And once a majority, this is crucial, once a majority of followers have acknowledged the right, this thing can commit it. But it is kind of, I guess, implied. I haven't actually read the paper, but it is kind of implied that if a follower is acknowledging write n, it means that write n-1 has already been acknowledged. So this is very serial. And this is a problem because if you have a database and you have like 10 tables, you can write to all 10 tables in parallel, right? Like it doesn't typically matter like the order in which you write to them. Like writing to the same table does have to be serialized, right? Because like, let's say one write is a withdrawal of money and the other is a deposit. Like maybe you first have to do the deposit and then you can withdraw, right? So within a single table or within a single page, I believe is the granularity, data, the writes have to be serialized. But in most other cases, they don't have to be serialized. So Raft is actually a bit of a bottleneck in this world, right? Like things are happening so fast with the RDMA and with the NVMEs that Raft needed a revision. So if we write in parallel requests R1, R2, Rn, they are processed sequentially by the followers. And if like for some reason one of the followers, like I'm doing 10 writes in parallel, right? And let's say write 5 for some reason, for some network connection, it got slowed. Like 5, 6, 7, 8, and 10 will delay on being acknowledged, and the leader will be kind of stalled until all these followers actually acknowledge. So that's a problem. And this kind of the same thing, like out of order requests also result in a problem because like if I wrote AB, but the leaders get them as BA, then like first B needs to be acknowledged, but then A, and like things like the leader gets a little bit stalled. So basically there are some problems with the classical Raft. So I just said the insight here is that databases don't really care about out of order writes. What they care is to know about the success of the writes, as long as they're just in different pages, but do not care about the order. So these guys went like the extra mile and developed kind of a revision to Raft, which serves their purpose. So they developed this thing called parallel Raft. Its structure is very similar of Raft, which is essentially a replicated state machine, which is a replicated log. It has leaders, followers, etc. But it does allow out of order log replication, which is what I just said. Like Raft enforces a serial order, parallel raft allows an out of order log replication. There's a slight difference in leader election, and then there's a process called catch up. Oh, so out of order log replication is what I've just been saying, that once an entry has been recognized to be committed, it doesn't mean that the previous ones have to be committed as well. Like I can commit write n even if n-1 has not been committed. So it follows a couple of rules for this to actually work correctly, like to prove correctness. If the write ranges of the entries do not overlap, essentially like what this means is they're not touching the same pages as I just said in the database, then it is safe to be executed in any order. Like I can change my name in this table and deposit money in this other table, and they don't really care about each other in general. Otherwise, they do need to be applied in sequence, right? So like in some cases, this kind of degrades to classical raft. But in most cases, it performs like this out of order thing, which allows it to be done in parallel. So that's out of order log replication. Then leader election in the classical raft, the way I understand it, essentially when there's no leader for a while, like the leader submit a heartbeat and the followers kind of hear it. So when the heartbeat hasn't been heard for a while, one of the followers randomly becomes a candidate. It summons an election and it is elected as leader, right? Like there are some corner cases to consider, but it is elected as leader. So in here, it is very similar, but the leader, once it is selected, it needs to merge all the logs, right? Because since the logs can have holes in them because of this out of order thing, it needs to do some merging steps. So it has this merged logic. And then catch up, essentially like if some follower is like really slow, it eventually might need to ask the leader like, hey, give me all these entries and I'll try to apply them as fast as I can. But it like plays this little catch-up game with the leader. So that's about parallel raft. So here are some like the design choices and lessons that they kind of expose in the paper. So some centralized systems like GFS is Google file system. It's a distributed file system. Contain a single master, which simplifies implementation a lot, but can result in a bottleneck because like if there's a single master, it is very likely that every single write, maybe not the reads, right? Like maybe the reads can be delegated somehow, but the writes probably need to go to a master because it has to do some of this bookkeeping. Then there are decentralized systems like Dynamo that essentially are a bunch of peer-to-peer nodes. So it increases reliability, but it is also harder to reason about, right? Like it essentially becomes like a more complex distributed system with more like moving pieces. So PolarFS uses a bit of a hybrid approach. There's a single centralized PolarCTL master, but chunk servers essentially work as peer-to-peer systems, right? Like chunk servers talk to each other. And actually the consensus protocol that I was talking about earlier, it works at the chunk server level, right? Like there, for each like chunk, there's actually two or more probably replicas. The paper mentions 3. So essentially there are 3 nodes or three entities that need to agree on the writes, right? So essentially the raft, this parallel raft protocol happens at the level of each of 3 chunk servers. So yeah, so these chunk servers are essentially like peer-to-peer machines. Snapshots from bottom to top. So PolarFS supports snapshots. So most databases that I know of, I believe, support the concept of a snapshot. Like you can kind of like, I believe it's like a copy of your database so that you can kind of like rebuild it elsewhere. Please correct me if I'm wrong, but it supports snapshots, right? But these are mostly implemented at the DB level. Well, PolarFS supports them so that the PolarDB logic can be simplified. So the explanation is kind of complicated. I honestly did not follow the whole thing, but essentially these snapshots are done in a way which does not block user IO operation while the snapshot is being made. So in some systems, it's like, hey, a snapshot is being made. I cannot take like any inserts. This thing does not work that way. This thing keeps the database like kind of more alive, let's say. And there's like a dance between Polar Control and Polar Switch and the chunk servers, and like it is explained in the paper. I didn't go that deep, to be honest. And then there's this third design choice. Sorry. PolarFS has a challenge of keeping its internal state consistent, right? With things like catch-up, while still providing a smooth service for users. So if one replica for whatever reason is lagging behind, it's going to start playing this catch-up game. And it is possible that for a very long time, that replica is kind of unresponsive because it's just doing this catch-up. But at the same time, like you want to still be able to use your file system because you have a database on top of it. You want to be running queries. So basically, they just developed this idea of like splitting these tasks horizontally. Like I believe it's like 128 kilobytes, like split across different machines. And I believe that way helps to solve the catch-up problem faster. Again, this is one of the parts that started getting like very technical. I didn't fully get it, but essentially, like because of its distributed nature, because of all the things that they've done in the hardware, PolarFS can be responsive to like a heavy data like user workload while still keeping its internal state consistent, which is very important. So yeah, we're almost done. This is just like to compare Ceph-FS, which is another distributed file system, with Polar with X4. So the idea here, these are X4 is writes to disk, right? So this is like comparing the performance of this file system, of this distributed file system, which actually just writing to disk. So the latency of doing a random write for this, for like a 1 megabyte block, is like, I don't know, 4,000 microseconds. For Polar, it is barely in the 1000, like it's 4x faster than Ceph, and it is just a little bit slower, like kind of twice as lower than writing directly to disk. Like this is X4 with SSDs, which are like blazing fast. So you can see that this is like pretty good. The same thing for reads, right? Like this blows this Ceph file system out of the water. Again, like the performance, the latency of doing a random read is very close to that of doing it directly to disk. And well, just more just like kicking this Ceph file system more while it's already dead to prove that PolarFS is like way better, right? Like its performance is much closer to writing to a local disk than other database, than other file systems. So that's essentially it. So just like to tie it back to cloud, the idea is that you can have a bunch of like relatively small machines, like I don't know, maybe like M1s, M3, I don't really know the naming, but they're not like super beefy. But with this, you can put a distributed file system on top of them, which is going to be blazing fast. In the end, you're going to have a lot of storage because you have this instant store from a lot of machines. And in the end, you have a pretty decent database, which runs on your cloud, thanks to this distributed file system, which kind of enables this with all this technology. So that's about it. Any questions?
Thank you, Ricardo, for great presentation. Now I see when you get a good paper, you're much more passionate to talk about it.
Yeah, the other one about the survey was kind of boring.
Yeah,
Sorry about that one.
No, it was great. So don't you think, anyway, I mean, just a quick question. Don't you think all this type of paper, they are sacrificing something to improve and other things? Like, for example, in this case, I mean, in the results, yeah, I see they're improving that the other one, the Ceph-FS file system, whatever it is. But at the end, for example, they are sacrificing a little bit of consistency, right, in the databases.
Yeah, I don't think the paper actually discusses that. But I mean, I think that I'm not too sure about that, because like the way the RAF protocol works is that once there's a majority of followers, that acknowledge a request, it is guaranteed that it's committed, right? So I guess like by definition, once it's committed, even if it's out of order, like you should be guaranteed to see it, right? Like to be able to read that thing you just wrote. So like maybe if there's like 100 people doing things in parallel, like, I mean, I guess the idea is that those 100 writes will happen mostly in parallel as opposed to having to be sequential. So I mean, I honestly don't know a whole lot about the consistency here. I guess this might be eventually consistent because of these holes. But in the end, like what databases support this out of order execution, right? Like if I do a write to table A and you do it to table B, like as soon as it's committed for you, you don't really care whether yours was before or after mine. So I don't know how much consistency is compromised. Like I don't know if this would be cataloged as an eventually consistent system, or like if it's something in between, right? Like completely consistent,
true.
eventually consistent. But nonetheless, like this kind of revision to Raft, I think it's pretty cool, right? Because you have this protocol which we know works, but these guys were like, hey, you know what? For this particular use case, we can actually relax it a little bit. Like it doesn't have to be that strict, and it still works, right? Like you can still prove the correctness of the whole protocol, which I think it's a pretty cool thing.
Yeah, true.
I think I would call it partially consistent. I think because in eventual consistency, it looks like, well, it sounds like at some point, all the nodes are going to have the same information, right? But I think in this protocol, it is allowed that some nodes have holes. It is they are called in the paper, and yeah, the node is not going to be able to like get that information. It is like a hole and in the log. But the important piece here is that if all the nodes like have the information committed, then you can assume that that transaction happened, right? It depends in the number of nodes that have that log committed in their logs.
But I think the way I understood the paper, I might be wrong, but the way I understood it is that these logs are kind of like are kind of like logical, and they're a transient thing, right? Like if the leader wrote entries A, B, and C, and for some reason A and B were slow, right? Like at that particular moment there was a network outage, but C gets there, like the followers will be like, sure, I got C, right? Like, and they will acknowledge C, they are a majority, C gets committed. So anyone who, like, if I'm like in my little terminal and I did an insert and that insert resulted in A, that might be delayed, right? But I will not see a commit. Like I will not get a commit back from the database. But eventually these things, these two writes, A and B, they should go through. So A and B, they go through. Again, we have consensus, we have a majority, they are committed. And at that moment in my terminal, I get the commit back. I get like, the acknowledge of the commit. And at that point, A, B, and C are in all the followers, right? Like, so these holes are in the sense that A and B did not get there. C got there first. So for Raft, that's a big problem, right? Like Raft needs to first commit A and B before committing C. But this protocol allows you to have the whole of not committing A and B immediately. Like my understanding is that they will eventually be committed. So these holes are not permanent. It's not like one replica will never have that, because then kind of by definition, you're breaking the protocol a little bit. Like if you have three chunks and it like you committed to A, but then B and C never committed it, well, that's not a majority, right? Like it will never be committed. So at some point they have to be committed in all the replicas. So I mean, that's kind of my understanding of the Raft protocol and of this parallel Raft. But I don't know, might be wrong.
Yeah, well, I don't know, because I also read that they use like, they consider the previous nodes committed, like they send like, what I understand is like they send like a request and they use a new data structure that contains the information of previous logs committed, right?
The back.
And they provide a value, right? The value n, and if that value, well, for example, if n is equal to 2, they just provide the previous 2 committed operations logs. But what if now they get a request, but how to say, an out of order request, but it doesn't like it is like the 4th operation out of order, right? And the node didn't get like the previous 2. Does it make sense? Like it is like a bridge that you are getting. You get the 4th operation, and presumably it is going to contain the last 2 operations. But what if the operation that was affecting the for operation is in the third position. Yeah, I don't know how to explain, but yeah, what I understood is that it can be false, but also I agree with you, but I think it can be also false, like permanent false in each node. I think. Well, that's my understanding.
Maybe. I mean, honestly, it started getting like a little bit too technical, and it's right here, this part you're talking about, the look behind buffer. So yeah, know that although several holds might exist, but can always be complete, like unless this condition is met. The follower can tell blah blah blah, which means blah blah blah.
Yeah,
Can be success. Yeah, I mean, I don't know. Like reading this, based on the above, the one that's storage semantic for databases can be successfully achieved. Yeah, log entry is not conflicting with any other, can be applied safely. So yeah, I mean, I think this kind of is what it says, that it needs to follow two rules. So here it is, the follows two rules. So I guess these two rules are kind of followed by this. This is what ensures that like the same page commits need to be applied sequentially. But the way I understood it is that replicas, like followers, eventually need to have the data, because like otherwise your redundancy guarantees are lost, right? Like let's say you have 3 copies of your data and one of them never got them, and you lose the other 2. Like in theory, like you like the RAP protocol does not cannot keep going if there's not a majority. But like if there's just one that actually holds the data, like I mean, you should be able to kind of retrieve the data from that from that one, right? But if it never landed in that one, then your redundancy guarantees are kind of like a lie. So I would assume that in the like eventually every log entry should be replicated to every follower, even if it's out of order. That's the way I understand it, but I honestly don't know. It might be good to like do a little bit more research. But yeah, this I don't know. I just thought it was a pretty interesting paper and concept in general.
Yeah, just one question, Ricardo. There, what is a TP system that it says there?
Where?
There in the TP, yeah. What is that one?
This commit semantics.
I mean, I don't know. Probably. I mean, because that's the type of system that allows not strong, like.
I have no idea. For example,
Yeah,
this commit semantics sets for search.
Yeah, because I mean, the interesting part is that I do remember that when going through Raft, one of the strong promises they have was like getting into the strongest consistency, like linearizable consistency.
Yeah.
But then, yeah, transaction processing system. So this is what allows it not to be strong. For okay, because at the end, the whole transaction is the one that, okay, I get it. Okay, yeah, now I follow you. yeah, I think.
Cool. Looks like you answered your own question after figuring out this acronym.
Yeah, I mean, I was like, but how? But yeah, I mean, if we are inside of a transaction, if it doesn't work, the full transaction, it doesn't matter if they went out of order, right? Because at the end you will roll back.
Yeah, I mean, this doesn't actually talk about transactional semantics, I believe. But I mean, my guess is that if you are in a transaction, like even like if you wrote 5 entries to a log, and like I mean, you can. It is possible that all 5 were committed by the majority, and you still roll it back. So this thing like that, I'm guessing that transactional semantics are applied at the database level, right? Not so much as the file system level. So essentially the database is, you know what, let me roll this back. So the rollback goes to libpfs. Libpfs is like, oh, we wrote to this chunk and this chunk and this chunk. Let me like undo those writes. So that is for the point of view of the file system, it's just like another write, right? Like a delete is just like writing zeros or whatever. But I would assume that transactional semantics are applied at the database level. And it doesn't really care about like the consensus that happens underneath it. That would be my guess.
Do you have any other question related to the paper, or can I ask some?
Yeah, go ahead.
Okay, so one internet, well, as Ricardo mentioned, this was possible using like the latest technologies in hardware, right? Using hardware in combination with software. PolarDB uses RDMA, which basically allows you to transfer data from the memory from one computer to a different computer, right? If you could use this technology in your computer right now or other computers, can you think of any application benefiting of this technology?
Yeah, we in fact do use direct memory access, not necessarily right remote memory, direct memory access. I mean, whenever you are reading an SD card, it goes through DMA. I mean, I do remember when I was programming like embedded systems, we went on to like reprogramming an SD card and doing DMA. Usually the way that it works is that you just like connect an SD, it connects directly to disk, it starts doing the transfer. The CPU only signalizes like, okay, just start the transfer and let me know whenever you are finished. But the CPU doesn't need to start like paying attention on like how the transaction is made, or even moving like block by block, or in this case, or chunks by chunks. So yeah, we're already using it, but I don't know, like remotely, it is like kind of crazy. I do remember that in our course, Maddie, we saw an example of Google using remote direct memory access to in a strong and a system that promised like a strong consistency or something like that. I don't remember.
Yeah, I'm guessing like NUMA systems can benefit from this, right? Like if you have like a bunch of machines and they kind of share memory, like if this like non-uniform memory access happens through this kind of hardware, that will make like the latency of getting memory from your own like local memory to getting memory from a different computer like much more negligible, right? So I mean, I'm guessing it's already like in use, but I don't know if these guys were like the first to think about using it for databases.
Yeah, I don't know. Well, yeah, this could be also used for machine learning, I guess. Like transferring data instead of files, you could just from one computer to another, you could just yeah, put it in the different computer and that computer could use it, right? Can you think in any other application, maybe instead of databases or machine learning, maybe? Or what about the security, for example? Don't you think it is kind of like worrying that one computer can update your memory with something?
I mean, yeah, it can be worrisome if it goes through, right? I mean, if I don't know, you connect. I mean, the simplest term is like you connect the USB and the CPU doesn't verify like its identity or whatever, and it just starts like doing the transfer, and there goes something corrupting your file system. Then, yeah, you're screwed. But I don't know. There.
Yeah, and like just to address that, I just found this. Redmark shows that current security mechanisms of IB, I actually don't know what's IB, here it is, InfiniBand, based architecture are insufficient against both in-network attackers and attackers located on end host. Not only secrecy, but also integrity. So yeah, it looks like there are concerns to like someone being able to read your memory without even having to go through the CPU.
Yeah, I thought that maybe just this could be a vulnerability for easier to attack, right? If you are in the same network, because it says that RDMA can be used for computers within the same network. So I thought that, okay, maybe one attacker inside your network can do bad things, right? But yeah, based on what you just showed, now it seems that also outside the network.
Yeah, I'm guessing there's like when you actually do this in your system, you do like a lot of access control, right? Like similar to like security groups in AWS. Like you are very, very, very specific about which nodes in the system can actually do this somehow. But I mean, this isn't actually going through TCP/IP, so it's not like you can block by IP. So I actually don't know how this can be done. Like, I don't know if like the RDMA protocol specifies like the name of the machine, like it identifies the machine somehow, so that you can like put on like ACL on top of it. I don't know, but yeah, it sounds kind of scary for someone to like get all the way into the fridge without without even opening the door, right? Like
Yeah.
they just
Without
face through the
breaking
door.
unit noticing.
Yeah.
Yeah,
So
yeah, but the
probably-
idea is that this avoids a lot of copying, right? Like usually like reading memory from the like, for what I understand, like the CPU needs to like read that memory, put it in a buffer, that buffer gets sent and like it gets written into another buffer in another machine. So there's like a lot of copying involved. So it's you are interrupting the CPU and you are causing it to do a lot of copies, which you probably don't want to.
It's kind of scary. Well, one question was related to the data structure that they introduced. The what was it called?
Behind
buffer. Yeah,
mhm.
but I don't know. I had the impression. Well, I had the understanding that it worked as I tried to explain that there could be holes, but then Ricardo also has a good point about no, it is. The logs are consistent eventually, so I don't know if I should ask it, but yeah. Have you used Livabe Cloud, or would you use it? It seems like it. Well, I haven't used it, but based on this paper, well, it seems that they want to compete, right? This paper, I really liked it, and I think it is interesting. So I don't know. Have you tried it? And would you try it?
I mean, I would try it, probably. There's always this concern with, because of Chinese legislation, of that always all of the companies that operate under the Chinese jurisdiction should allow the Chinese government to look into whatever they have stored. So that is a concern. I mean, the same happened to Huawei. So I don't know. I mean, as for me, it could be like if it has like more nice stuff that I can play with, it's okay. But for my client, probably they can like. Yeah. But it does say it's cheaper. I was just reading.
Yeah, and also they had a good market share in previous years, even above Oracle's cloud. So I was like, maybe it could be cool.
Yeah, I don't know. It would be interesting to see how many Chinese-based companies use AliCloud, right? I mean, probably like if most of them, I don't know.
Yeah, this is just talking like about the security of the applications, which is all nice and good. But then maybe you don't want the Chinese government like actually looking at that, because I mean, they're not breaking your security, they have the right to do so. So yeah.
I think that's
most of the time, like at the end, they would force this type of companies to host the data in the different country. To host, for example, US data in US border. Like the thing that they were trying to force TikTok to do. So same stuff can happen.
Yeah, I mean, I do have a client that has forced us to move most of its information to the European servers. I mean, it was like a ultimatum, is like, you do it or we're done for. So, I mean, I don't know, probably, but again, I don't know, for example, what Huawei, I mean, I do remember when we had the Huawei argument like 4 years ago, something like that. It was okay, they had like, their devices were not even being made at China anymore, but Huawei, because of some political stuff had to actually still send information to Chinese servers. So I don't know. I mean,
Hard to say, really.
Yeah, I read something that there was some code in, I don't know, Huawei or some smartphone. I honestly don't remember, and I don't know if it was true. But that whenever you wrote something that looked like a credit card number, some people were like sending that data over like to God knows who, where. So might be like a hoax, like Pokemon gives you like epileptic attacks, but I don't know, maybe it's true.
Okay, let's wrap this up. Thank you, Ricardo. Thank you,
Sure.
Luis. I just want to have time for the next one. So I think we can't go for the break. Just let's continue with the next paper. Juan, you can start sharing your screen.
Yeah, it is me. Hold on, please.
Yeah, sure. Yeah, sure. We can see.
It is moving now, or it's not moving?
It's not moving. We are
Okay.
seeing the actual. We are not seeing the presenters. No.
Yeah, it's happening the same thing. Yeah. Now it moves.
No. We can see your yeah.
Yeah, I'm trying to
Yeah, that
like present first and then share the screen. So
Yeah,
you
now it's-
know exactly which screen to share. Because you are showing the, what's the name? The PowerPoint one. So the PowerPoint, not the presentation.
I think you can see it now and it's moving. now.
yeah.
Yes.
All right, all good.
Yeah.
Yeah, go ahead.
Okay, so hello everyone. It's my turn this time. Okay, well, the paper is named Green Sustainable Cloud of Things, Enable Collaborative Edge Computing. Well, basically, this paper speaks about a lot of things that the paper describes as a next stage from Internet of Things. As well, describes a little bit about edge computing, and also is setting up a problem. There is actually a problem of optimization, and that is the big chunk for this paper. Okay, we have 4 contents: introduction, research, directions for edge computing, color things, the problem formulation, and future research challenges. Let's start with introduction. First of all, I need to present some terminologies since several names are too long. So we will make it short. It's also the same terms that are indicated in the paper: wireless optical broadband access networks, wireless mesh networks, optical network unit, optical line terminal, passive optical network, edge device, network function virtualization, software-defined networking, virtual network embedding, and green sustainable virtual networks and a virtual network. Okay. As I said before, this paper talks mainly about Cloud of Things. Since Internet of Things is providing a lot of cloud services, so this means that it will increase the capabilities of connections in big distances. And it will provide a lot of big data exchange. So there are several challenges to solve in Cloud of Things, like bandwidth saturation, energy constraints, low latency transmission, and data security and privacy. Many of us, we are already familiar with this kind of problems and terms as well. And edge computing can help us to solve these kind of issues. But we have to explain as well, what is edge computing? I'm pretty sure many of you and us, well, not me, this is actually the first time I heard this term, but edge computing basically is to place the processing power as close as possible where the data is generated. So since the devices are closer to the final user, the data exchange will be much more easy, and something that will improve really good, it will be the latency. So it will take less time to make the exchanges of data and any other services that we are using at that moment. The possibilities are multiplied, and basically all the devices are close to the, like a new cloud, that it will be the edge, the device that is in the edge. That is why in the edge, really like about to fall down from a cliff or something. That is how I understand it. Okay, some of the benefits that we have here is low service cost, high computing capacity, and competitive system scalability. Our services will decrease how much we pay for them. The capacity of the computing, it will increase, and we can escalate the system really easy. It is important to observe or take a note of it, that according to Cisco, with the advance of Internet of Things and the post-cloud era, which is Cloud of Things, around 50 billion of things will be connected to the internet, and it will increase each year. 45% of the data will be handled by edge devices, which points out the importance of edge computing. And 50%, it will be an increase of 53% in data annually. Now, this is like a diagram of how a wireless optical broadband access works and how it connects to everything. The generated data is forwarded by routers by wireless channels, and it's received by neighbor optical network units. Then an optical line terminal will receive the sensed data, and it will receive it through a passive optical network. And according to the obtained information flow, then the decision can be made in the central office, and it can connect to, I don't know, maybe to a business, to a home, or an industrial center as well. With high volume of data, we must prevent data saturation. So an edge device can be deployed in order to alleviate all the resources that we need to deal with this data, again, on the edge. Also, it will be a collaboration with the ONUs in order to keep solving this problem of data saturation. And there is a growing volume of data being generated by these devices. So as I said, to elevate the resource provisioning, then wireless routers and ONUs will collaborate. So there is some research direction for edge computing. Well, basically there is for edge computing provides, edge computing includes various technologies, and there is promising research direction for it. The first one is edge computing over weapons. Why? Because sometimes the latency is unacceptable. It's around 30 milliseconds and or 100 milliseconds, and this is not a good idea for some applications like autonomous driving, or some of us that we like to play video games. This latency is not very good. So it will be better to place or deploy some edge devices close to us if we want to play, or in this case, close to the highways or any roads where the automobiles that drive by themselves are. Also, cache-enabled edge computing, there is a problem of placement and delivery. So these are the core issues. So service caching is for resource allocation. So in the traffic wired internet, a backhaul and mobile core networks can be reduced by deploying caches in base stations, relays, and user devices. Also, collaborative edge computing is not possible for a single edge device to do all the tasks. So it is important not just have one, have several as well. Works together with PONs and optical data, optical cables as well. There is some privacy concerns because effective incentives and privacy preserving schemes are necessary for it, and for data sharing as well. They can be used for healthcare. And the last one will be virtualized edge computing. Costs can be reduced because we can use virtual machines to do all the work. Flexible management of computing resources need to be coordinated. So network virtualization is an alternative because it's really, well, everything is virtual, you know, there is no physical stuff, so that our costs are reduced. Now, I think this is the core or the big chunk of this paper, which is the problem formulation. Okay. First, we need to analyze why the authors propose this kind of framework, or this green sustainable framework, because edge devices are likely to lose efficiency, as it says here, for channel interference. So the process information will cause big delays if one of the edge devices fails or something like that. So basically, this is like a mathematical problem. I saw it as an optimization problem, something that we built in the past, you know, the shortest route and that kind of things. And this is the definition for each variable. Total number of WMS and IoTs, total number of BNS, the number of embedded virtual networks processed by WMNS and IoTs, number of BNs processed by the PON that are in the backhaul, this variable is like a backup because the main one is N1. So we will see in the algorithm that if the principal, one of the principal fails, or the option that the algorithm chose as the best route to follow, I don't know, something happens, you know, a line was cut, an accident, I don't know, and things can happen. Then the algorithm will choose the backup, which is N2. And those are stored in the following variables. I don't remember the name of it, but it's like a Russian letter. So we call it a Russian R, which is the backup and the working backup and the main backup. And a binary variable to identify if the virtual network is inside of not or not of the WMN. Okay, as I said, this is like an explanation of how, like a small model, all the variables, and which is the objective. That basically is to minimize the transmission power and maximize the sharing deployment. So WOBAN has n number of WMN and IoTs. This is actually, I need to read it one by one because it's like some steps. So MI has stands for edge devices. P is for wireless routers. M and P are sets of edge devices that are connected to the O and U. And the current virtual network can be expressed in the model that you see on the screen. Virtual network is equal to virtual node that multiplies S, P, WB, and C. The sets of edge devices connected to the O and U are S, and wireless routers are Phi. The radio bandwidth stands for WB, and computer resources are C. Then the virtual nodes must be embedded to the graph. And then an edge device is connected, need to connect to working on O and U. And then an edge device connected to the wireless routers is needed to hold all the other virtual nodes. So the mapped edge devices will have more computer resources than normally is required for virtual network serving. So the bandwidth of wireless channels for link mapping should be larger than the consumed bandwidth for mapping. So now the model will be changed. So a virtual network, now it's equals to each virtual node that multiplies EW, S, P, and C. Now, as I explained before, all these virtual networks must be embedded to, this is the backup. This is the Russian R for backup. And in order to connect to the edge device will be the highest sharing degree. And M must be bigger than C. And once the mapping is done, now the sharing degree will be equal to a virtual node. As I explained, the variable N1 is a virtual network processed by WMN and an IoT. And the binary variable that we saw before. And the objective of all this is to minimize, as I said, the transmission power and maximize the sharing degree. That is the objective. But they basically, this is how I resume all the problem formulation, because they were basically explaining all the steps that they need to do to achieve this. And well, this is the objective. And that is why they do the model. We must minimize the transmission power for each backup source of sharing degree. And as I explained before, there must be a backup, and this is N2. And it will be a virtual network that is actually processed by a PON backhaul. And the backhaul carriers is equal to WB, that is multiplying BNA. Objective, minimize TP and minimize N2. Why N2? Because it's the backup. Also, it has to be the lowest. We want to save energy. So if, as I explained at the beginning, if the main option do not work for something, it has to grab another one from N2. So that is why both of them have to be minimized. Now, this is actually the heuristic algorithm to solve this the previous problem. This is divided in, you can count here 5 steps, but it's actually 6. So this is like the resume of the algorithm. As well, there is a part where I have to explain everything step by step. So, well, the first step is initialize the corresponding information of the WOBAN and BN according to the network status information. Means that we have to check which virtual network, which is the status of each virtual network that we have to embed it. Yeah. We must confirm the amount of backup edge devices at each WMN and or IoT according to the formula. We need to count how many edge devices we are counting on, you know. NPR stands for edge device failure probability. That is why we use that formula, because it will help us to understand which are the chances of our edge devices fail. So residual edge device of available wireless routers for working resource units. If more edge devices are deployed, the key value will increase, resulting in a higher network reliability. So if the failure probability is minor to 0.5, the key value should be increased. So the edge device failure probability decreases, and this is under threshold. And for all U that are inside an M and for all B that are inside an P, this is a condition that must be accomplished. B stands for backup wireless routers, and U stands for backup edge devices. So now we need to satisfy the locations of the O and U edge devices and other wireless routers with the conditions that I said before. And U and B should not be more than the maximum location of an O and US. The sources must be divided into parts according to a scaling factor, and the backup edge device must be deployed, otherwise the initial value will be 0 and it won't count. And actually the algorithm remove these all the values of 0, which is not convenient, because if, I don't know, for some reason something's wrong and the best route is 0, it will be taken out and it will choose another option it won't be the optimal one. So the qualified WMN or IoT for a virtual network must be selected. Each WMN or IoT lower than C is removed. This is why I was speaking about. The channel of UMB is updating, decreasing the value of the channels. Channels with value 0 are removed. And the sharing degree channel with the higher value will remain, and that will be chosen. So if the sorry, this is autocorrector channel, that's that. The route with the highest sharing degree will be the one that has the optimal value in order to use the model. And for the last, after that, N1 will increase by 1. And if the virtual network was not processed by the WMN or IoT, a backup, each device must be chosen. Then N2 will increase by 1. This is what I was speaking about previously. If the main option was not eligible, then we have to choose a backup. And if everything fails, the step 5 will start again to choose the best channel. Now for the performance evaluation, the authors chose, wait up, I have some notes here. Okay, the authors chose a map of the US Davis University for this evaluation. In this simulation, each WMN or IoT has the same numbers of edge devices for simplification, as you can see in the image. This is the first graph where we can appreciate how they measured the model. Basically, the upper line is the one, it's not the model. The lower down is the line of the model. It says we can observe the total transmission power that is needed to embed virtual networks. So you can see, it's really easy to see that the model of the authors is more efficient because they require less energy to actually take the same amount of virtual networks and place it and embed it. So it's basically requires less power transmissions and more VMs, more virtual networks are embedded. So it works. And the second graph, we can observe that the green sustainable virtual network without, this is the factor that I was speaking about, has a bottleneck. And it has not enough resources to embed all the virtual networks properly. So that is why the number of virtual networks in the system increase, but it actually happens anything. It happens anything. But with the model of the authors, we can see that they can do it. So basically, it works. Now we will speak about some research challenges. Well, the first of all that we need to speak about is security and privacy. The challenges for future research are that efficiency is being lost, and some warbands can cause unconventional authentication, difficulty on judging if the edge device is an attacker or actually if it will help to the system. So it's hard to identify it. Vulnerability. Virtualized infrastructure at the edge is vulnerable to privacy invasion. So, and this can be caused by virtual machine manipulation. It is important to provide secure connections for all the devices in the cloud of things. Scalability and energy efficiency. Extensive connections in cloud of things can generate huge network traffic. So if we don't do this kind of optimizations in the system, the energy will deploy really, really fast. So that is another reason why this model is sustainable. Besides, we use less power, it lasts longer. And the next one is data abstraction. Well, some of the challenge are the formats of the delivered data from services are several. A trade-off has to be made between the degree of data abstraction and data storage, and how to extract useful information reported by the various and unreliable edge devices. And different applicable operations coexist on edge devices. And the last one is catching at an edge device. We must to alleviate the constrained bandwidth of the backhaul. So we can predict the user preferences. So we can know why, what things they are interested in, and everything can be catched beforehand. There is already some data mining and machine learning techniques that are already being developed. But the main problem is that predict everything at a big scale still is an issue. So it's something that it's important to work on. And well, the conclusions for this paper is that basically the proposed framework showed up that it's possible to embed a lot of virtual networks with the maximum sharing degree and the minimum backup resources, or the minimum main resources compared with existing models. So high energy efficiency can be achieved. And Baswell points out the future of Cloud of Things and research, and why edge computing is important along with the Cloud of Things. And thank you very much for hearing my presentation.
Thank you, Juan. I understand it's how to say, when you pick a technical paper with math inside, then it would be hard to present it, because I mean, it takes time to understand the maths, and it's just difficult to really get in a short presentation. But anyway,
which are the things that you are looking for in a paper for selecting from the
anything
suggestions?
that you there isn't anything that I look for. I mean, anything that you're related, I mean, you are interested. It shouldn't be technical necessarily. It shouldn't be.
Yeah, but for
math.
example, if you are presenting 3 papers, 3 suggestions, how do you select the one that you are going to present?
I usually look at the authors, journals, and that's it. Which journal it is coming from and which authors. Mainly journals, citations, stuff like this. But nothing about the number of the page, or it does have math or doesn't have. Not really. It just certain papers are better paper than others. I mean, it's real. Okay, it's not all the papers or all the journals are equally valuable. So when you suggest 3 papers, then I try to find the one that I feel is more credible and it's more interesting, or more, yeah, that one is more credible.
So
Okay,
more questions.
Yeah, sure. Sorry.
Yeah. Well, from the paper, first of all, before asking my questions, anybody has any questions or topic that you want to discuss about this? Nobody? Well, then in general, I know that he mentioned part of the objective of this paper, but what everybody thinks that it was the main objective of this project. Because when we read it, like I was discussing with Juan, and we were understanding some different things. So that's why I'm asking to the others, what do you think that is the main objective of this project?
The thing that I really don't actually get is that, I mean, I do understand that they want to optimize transmission power of all of the end devices before they get to the optical network unit. But I don't understand. I mean, do we want to have how do you do this? Tuning them to have the less power, or by better distributing the end devices? Or, I mean, whenever they started talking about the virtual networks and the end devices and the transmission power, I got lost. I mean, I was
yeah.
What do they even want? Right? Yeah.
That is actually mostly the purpose of the whole paper. Yeah.
What do they tune? I mean, they tune power. So they went on each end device and say, you just need you don't need that much power. So let's just tune it out to less dBms or milliwatts or whatever. Or did they, I mean, that's the part, at the end, what did they optimize?
Well, they're trying to minimize how what I understood about the paper is that they are sending a signal, and they have a big network, as you saw in the picture, with the red and blue small devices.
You can show the picture.
They have. You can show it. Let me show the picture. You can see it, right? Okay,
Yes.
what I understood
Yes.
about the paper is basically which is the best route to follow to achieve your objective. So that is why it's a problem of optimization. They try to measure from which is the line with less transmission power, and if the devices are available or not in that path that the signal has to follow.
Okay,
Basically.
okay, I see. So it's more like a path optimization in the sense
Yeah.
that you need to take those optical fiber length segments that are shortest while also being available to get less transmission power, right? Or something
Exactly.
like that. Ah, okay.
That is basically the whole point of the paper. The paper, yeah, spoke about, yeah, it's really important kind of things and future research challenge. But the purpose of it was to explain this, how to do it. And that is, I really had a really hard time. I also talk about this with Maddie, that maybe I shot myself in the foot with it. But yeah, basically that is it. Choose the best route where the signal can flow to achieve the final destination. And that is why we need to calculate the transmission power. We need to minimize the cost, calculating the edge devices, and also the wireless mesh networks. In that way, the algorithm can find the best route to follow. Maybe, I don't know, there was an accident, and instead of, traveling by here, they need to travel by here, and then this and this and do this to achieve the whole. You know what I mean?
Yeah, I mean, the thing is that I think the most difficult part of the paper is actually going into like most of the terminology.
Yeah.
Because I mean, they go into optical terminals, optical network units, and interchannel interference, and I think they even go into power spectral density and probability. I mean, those.
Yeah.
I mean, nice those in the career. And when you were, when we were going into the paper and you were talking about them, I was like copying tabs all crazy, reminding all of the acronyms. I mean, it's just crazy.
Yeah, I shot myself in the foot.
Yeah, I mean, no, it's not like that. The thing is that I think that as with almost all of these more oriented telecommunication papers, you get lost in calculations. I mean, yeah, that's a big problem. But I guess that we can all agree that this also has to do a lot with end networks, right? And a lot of what we were seeing last class regarding like environmental awareness, because I mean, we always want
in some part.
Yeah.
In some part, because actually I was discussing about that. Well, I think, in my opinion, at least, yes, consuming less energy. But for example, also I have questions about costs, for example, and how to select, for example, the endpoints for the optical fiber. Because I was like, okay, how do you select that? Like, for example, there are some places that in some condominiums, they have optical fiber until the condominium, right? And then there are some places that optical fiber arrives to your house. Then in other places, it arrives to your modem, right? Yeah. So what is the advantage of having it like on each step, right? And also, I don't think that this algorithm considers that part, right? Like exactly in which I think that when the endpoints of the optical fiber are established, this algorithm works, but it doesn't say anything about how to place physically the optical fiber endpoints, right?
No,
doesn't make it.
Yeah, that's the most difficult problem especially for PONs that are like passive optical networks, in which the last mile problem. In telecommunications, we call that the last mile problem. So basically you got the fiber all the way closest to your condominium up to the OLT, that is the optical line terminal. But if you right there then take like a copper cable and then get internet from copper cable, then all the effort that was put in bringing the network using optical technology is lost, because you have like this huge bottleneck at the very end, and that problem no one. So I mean, in Mexico, I mean, when all the time optical fiber is unavailable, rats like just eat it and they steal it, and yeah, it's
Yep. Yeah, actually, that's something that I was discussing with Juan before he present. And so, well, I don't know if anybody has more comments about this right now, because otherwise I will ask another question that it's related but not related to the paper. So, nobody? Okay. So something that I was wondering when I was reading the paper and when I see all the mesh, like all the networks, is I wanted to ask the opinion of everybody about what do you think about having so many local networks, so many devices that are wireless? Do you think that all these how do you say signals could damage your system, like healthy wise? What do you think about it? Like, do you think that probably they are not affecting, or are they affecting? Because each time we have more devices, right? Internet of Things. And before it was like, don't sleep with the cell phone next to your head because it can cause you so many things, right? And nowadays also the technology has been changing, but now you have like the cell phone, like almost the earrings, you know, like the watch, you know, you have a ultimate, like when you are exercising. So all the time, constantly, you have one IoT device close to you, even if it's not yours, somebody has it, right? So do you think that probably in 30, 40 years, this will cause problems and people are start having issues because of this? Do you think that it's affecting or no?
I should say something. It might sound a little bit bad, okay? But I mean, there are evidences, okay, that I mean, there are proof that it doesn't affect, okay? So there are studies that they prove. I mean, if this type of basically frequencies and signal they want to affect you, you have to be, for example, go and hog its really cell tower for a couple of decades, you know. So it may be dangerous, you know. So, I mean, the amount of exposure we have is not really. Actually, just a couple of years ago, 4 years ago, yeah, the PhD students here started, he did a PhD on it, okay? And they did measurement with 5G devices, with all sorts of experiment that you can imagine they did. And basically after, I mean, I remember at the first proposal defense, I said, it is already out there. I mean, it's not, I mean, the study is basically redundant. I mean, it doesn't affect, okay, but he was insisting, and the advisor was insisting that they want to do the study and measure and everything. But at the end, after 4 years, I mean, they said like, no, I mean, it doesn't affect. I mean, I don't question their study because of the 5G, especially the new technology, millimeter waves that they are getting more. So it had some point to do the study, but it doesn't affect.
So
we'll see, because there was a time where cigarettes were recommended for pregnant women. So
actually,
nowadays we know that that wasn't right.
Actually, they're having a lot of medicine that they have been like for 50, 60 years on the market. And they did a study before launching the medicine for 10 years to see if they have any consequences. They said like, it doesn't have consequences. 40, 50 years later, no, it was cancer, you know, because in short time, it doesn't affect, and in low volume, it doesn't affect. But then they didn't know that long term and higher volume, it affects.
But this is a polemical topic, right? Because we can know to, in this case of teens, we can know to a short time, but we can never know how something is going to act for the long time. But
you can actually, I mean, you can do the study. I mean, not. My point is, for example, this type of effect should show, you know, like a massive jump. For example, you say from the time that we started having 4G. I mean, there is a time period that we started having 4G towers, right? Then how many years passed? Like whatever, 10 years passed. Okay, now let's do a study to see if there is a major change in a special health situation, health-related situation, comparing to that 10 years ago. But if you're referring to like, what about like next 100 years? I mean, who knows, you know? But apparently, I mean, anyway, the studies with animals, with stuff like that, they prove that the level of exposure that we have at the moment is not damaging.
I do think that also, I mean, if you go like strictly into scientific way, those ways that could actually bring harm to us would be like the worst would actually be visible light, because visible light does contain tons of frequencies, and some of those have a wavelength that is smaller, comparable to the space between our molecules, and therefore can cause a mutation. But as for long wave radio, shortwave radio, millimetric waves or microwaves, those that are used in 4G and 5Gs and like in the national spectrum assignation square that we keep in Mexico, those those have very long wavelengths and therefore can't go through us. I mean, that's basically how, I mean, we should be more aware of visible light, because since visible light has all those frequencies embedded in, some of those can actually harm us. I mean, that's why people are getting skin cancer, because all of those frequencies are contained in visible light, but nothing like millimetric waves. Those have like huge wavelengths.
Yeah,
I mean,
Fernanda, go ahead. Sorry.
And I mean, at the end of the time, we are not going to stop using those
Yeah.
devices just because of that, right?
At least not today.
We're still going to use it. It's like when the people say, hey, cigarettes are going to